Good morning, everyone. Today I'm going to present a paper titled Auto Split, a general framework of collaborative edge cloud AI. This paper is published on KDD this year. So here is the outline. First, I will introduce the motivation and some backgrounds, and then I will introduce their proposed framework and show you the experiment result and finally conclude the paper. So, I'm sorry. So since most of the data nowadays are collected from the edge devices, so the machine learning application are preferred to deploy in the local device itself. So, however, since the edge devices has limited computing and storage capacities, so that normally if the model is very small, the paper was saying that if the model is smaller than a particular size, that is preferred to deploy in the edge device itself. However, the state-of-art deep learning model are typically larger than this size, so it's basically impractical to just deploy the whole networks in the edge devices. And the alternative way is that we can leverage the cloud computing to help us do the model inference. So the edge will send their raw image data to the cloud and wait for the final result. And since sometimes uploading the raw image to a far distant cloud will be very expensive and the end-to-end latency will be very long. So the cloud solutions only support some of the model that the intermediate activation map may be larger than just transmit the raw image data. So if uploading the raw image data can be very expensive, so the cloud transmits the image to the cloud may not be a feasible solution. So it turned out to be the second alternative approach, which is we want to split the model into two subnetworks. One is stored on the local devices, and the other one can be continue computing on the cloud. And this type of solution is typically suitable for those networks that their activation map was, the size of the activation map is much smaller than just the input image. So we can reduce the transmission cost and also leverage the computing capacity of the device and the cloud jointly. So it's much more practical and affordable for the edge device to perform the state-of-art deep learning models for their applications. And in this paper, they focus on this second solutions there. So for the second solution, the main challenge to introduce the edge cloud collaboration is that we need to split the model, which we can achieve the minimum end-to-end latency. So, So the first method is called the Chen-based network splitting. It's that we can see the network as a chain root, that the layer will be connected layer by layers, as shown here. So there are some previous works has been done to break down the networks. For example, like here, the VGG, they basically break down the layers and to to analyze their computing and the communication latency for each of the layer and try to identify the optimal layers that to split, and so that we can have the minimum edge local computing stage with the smallest transmission cost. However, this type of chain-based method has the drawback is that not all the networks can be represented by the chain-based. More complicated networks are better presented by the graph. So more popular way is to consider the networks as shown here, like the directed aclinic graph based method. So we basically represent the network in this way. So using the graph, we can use some optimization algorithm to identify the minimum transmission cost to send the smallest intermediate map to the cloud to do the computing. However, this kind of existing work do not consider the local memory constraint. And also they assume that the local would have enough of the computing to support the high precision operations. So they kind of missed opportunity to further reduce the computing cost. So in this paper, they trying to combine the quantization with the graph-based splitting method to propose the new edge and the cloud splitting approach called the auto split. And next, I will introduce their proposed framework. So basically, we have a well-trained model, can be a very big models, and also we have certain kinds of demand. For example, the user would can specify their device as the memory and what kind of bit representation they can support to do the computing. And also they have the requirement for the model prediction accuracy. And also they have the way that need to connect to the cloud. So they will specify the wireless networks they are connected to. So based on their requirements and the well-trained model as the input to put into this auto split schemes. And then based on the algorithm, they can output a quantized split network where they tell you the layers that you need to implement on the edge device and transmit the intermediate data, and then to wait for the result from the cloud. So this is the overall framework. And for in this type of framework, they first define the objective function, which is the minimizing the end-to-end delay. So suppose that the networks are split at the layers end, so the total latency will decompose into 3 parts, including the edge computing, and plus the transmission cost, and plus the cloud computing cost for the rest of the networks. And to consider this type of question, we always have 2 feasible solutions, which is the cloud-only solution and the edge-only solutions. So the cloud-only solution, as we can see, they represent in this notation. The 0 represent that there's no networks layers are going to store in the edge device, and BW and BA will represent the bitwise for wait and the deactivations. So to minimize this objective function is equivalent to minimize this formula, since the cloud-only solution will be a constant number because we deal with the well-trained models. So after some mathematical transformation, we can rewrite the objective function as follows. So it's basically.
So here I have a question here. So if you see the objective here, you see here the Li edge, they sum over from I from 1 to n. So I assume that this means that this is sequential neural network, I mean not a sequential, it's sequential neural network architecture. But I think before you mentioned that, well, we should model it as a graph, right? Not a chain. Now, if you see the objective here, this is more like a chain, so that you can sum, you just add the latency at each layer, right? So it's more like a sequential processing. So what happened here?
I think you can see as a type of index. I don't believe it's typically sequential here.
But you see here, right, that the DNA is split at layer n, and then this layer, yeah. Can you go back to the figure to show the network architecture? The graph, yeah, this graph. You see here, how do you divide it into n layer? Let's say give the figure 6. Right, the first layer is very simple to understand. The last layer is very simple to understand. But in the middle layer, for example, the V7 and V8 and V9, are you going to categorize it into the, for example, the second layer, the third layer, or the fourth layer?
I think the I here, I think it's more like the index in each of the layer. So you need to put the index for each of the layer as here. But I don't think the computing, like the order is kind of sequential, because you're not going to compute the V7 after the V6.
Yeah, because this is, so that's why my question, if you check it carefully, looks like, those different branches, they are processed in per layer. They are not processed in sequential, right? So if that's the case, if you want to calculate the total computation latency, perhaps you want to get the maximum instead of just sum them together. If you want to calculate the accuracy, the latency.
Okay, I see.
You get our point?
Yeah, I see your point. And I have to say, I think they do not necessarily explicit this latency function, because in the experiment they're using the simulator to measure. For example, if we want to calculate this latency, they will measure. For example, like here, they will break down each of the layers latency, like here. Even if it's not Chen, you can still do the breakdown for each of the layer. They actually do in the experiment.
Another quick question for this graph. What do you mean by the high latent V5, V3, VG, V9, and V12?
I'm sorry?
What's the graph want to show here for the highlighted node? For the highlighted
node? I think it's just the symbol to show, like, I think it's for different operation. It's not highlight. I think probably here you can see as the convolutional layers, and next you will do like batch normalization or something. I think it's for.
Does this mean now this layer working on node 5, node 3, node 9, and node 12 right now? And probably next layer we're going to work on node 6, 7, and 8. And the next layer we're going to work on, I don't know, 10, 11. Finally, we're going to work on get some summation or something, aggregation or something like researching?
Actually, I'm not sure for the color represents which part.
The reason why I ask, because you're using directed a cyclic graph, right?
Yeah.
Because you can now say, I randomly pick up the nodes to work on that. You have to follow the directions. Otherwise,
yeah. So here it's the input side, and then this is the final output, I believe, or for certain kind of big layer. So you have the input, and you have this output. Here it just like showing in the figure 5. This is the convolutional layers that connect to.
I think one way that to figure out is to you check the InfoComp paper. This InfoComp paper, I think they should have some kind of formula to calculate the latency, because if you consider this directed graph, actually computing the latency will be a challenging problem. Actually, it will be complicated. So I assume that if you check this paper, they will formulate this problem as for example, NP hard problem, because this is the integer programming. They need to decide which neuron to partition. So in this case, you will be able to see how do they formulate the latency. I think the latency formula that you show us later, actually perhaps just a very is an abstract form. But if you want to see the detailed form, perhaps this InfoComp paper will give you a better idea. That's just my guess. Okay, but I think that's the case.
Yeah, I think this is the case. Yes, for this is a very high level formula for the latency. So the following optimization, they do not explicit this. It's basically a black box function.
Oh, so do they? But they still need to load the objective function in order to do the optimization, right? Or do they use a reinforcement learning or things like that?
Since next I will explain, because basically they have this kind of constraint. So I can continue, then you can.
Oh, okay, I see. Mm-hmm.
Yeah. So they kind of reformulate to this type of question. Basically, you just compare, if you do the splitting and compare with the latency in the cloud-only solution here. So they also introduced 2 constraints, which is the local memory constraint to store the layers, and also because they are consider the quantization. So the quantization arrow towards the model prediction accuracy is also considered as the constraint. So here the challenge is that they do not they see the latency function as a black box functions. So what they are doing is they are trying to propose a multi-step search to find the potential possible solutions to satisfy those constraints, and they will pick those the solution that have the minimum latency based on the empirical measurements. So the first step is to first do the graph optimization. Particular way is that they kind of optimize the operation here. For some of the layer, they can fuse to one layer, since the operation can be done simultaneously. For example, after you do the convolutional operation, you can next do the batch normalization and do the RALU. So actually this layer can be fused as one layer. So as shown in the right figures. And so after the graph optimization, we can find better solutions as they claim. And after, based on this optimized graph, next one, we are going to list the potential split point, which based on this DAG graph. So you can see the node as each of the layer, and the weight is the transmission the transmission size. Basically, you can assign the smallest bit and times the activation size. So in this way, you can either use this mean cut optimization problem to find the minimum cost based on this graph networks. So perhaps you can find multiple solutions, or I think the purpose they can also use is you trying to identify those layers. If you do the cut, you can find those transmission latency that is less than the just transmit the raw image. So you can list all these potential split points into a set, and you can describe the set in this following ways. So not only they consider the transmission cost, but also they consider the layers that are going to store in the edge device should smaller than the memory cost. So this is two type of rules that you can identify the potential split point. And for a specific split point, for example, we split the layers, and we can see though those layers are going to store in the edge device, they are going to assign the bit representation for each of the layers. What they're going to do is, instead of just seeing the constraint, they are going to reformulate and solve these two sub-problems. And D here is the way that they quantify the quantization error as the mean square error compared with the 60-bit weight representations. So in this way, they say that if you solve the problem 8 and the problem 9, you can find those potential solutions, the potential bit representation levels, the quantization levels, that then you will have to verify their accuracy drop. So as long as the accuracy drop is within the requirement that the users are set, so you can keep those potential points and the corresponding bit representation in the possible solutions. And then based on the network conditions and the edge device computational capacities, you can find the optimal solutions. So this is.
So what is the difference between SIW and SIA? You say that there's a
SIW is the storage for the weight. SA is the storage for the activation.
If that's the case, why is sum over I? Another one is maximum over I.
So basically, you have to store all the weight parameters, but for the activation, I think you can, like, for example, like cache, you can replace for the newest one. So you don't have to store all the layers activation. You just have to store the last layers, I think, for the next computation.
So what is the B mean?
B minimum means the minimum bitwise that can supported by the edge device. For example, if the devices can support int A operation, so the bit mean here is 8. Or you can say lower operation like binary, or the B mean here is just 2. So it's depending on the edge device. How can they support the bit requirement?
Okay, so can you go back to the previous slide? Here, so the quantization is done on each layer, right? So you use 2 bits to represent, for example, 2 bits to represent the layer C. Does that mean that
only, sorry, the 2
does that
represent the activation? Yes.
Yeah, I'm thinking about so the activation, I mean the activation quantization level determine the transmission size, right?
Yes.
And the weight quantization level. So if you have, for example, if you have a 2-bit quantization for the weight, so in this case, do you mean that the output will be 2-bit as well?
It's not necessary.
Yeah. So, but after 2-bit quantization, 2-bit activation, the output will be 2-bit for sure, right?
Yes. I think the purpose is that, for example, for weight, the quantization is not only affect the memory, but also affect the computation, right? So perhaps the convolutional layers, you have this output is probably 4-bit to represent the values. So if you are going to store this value, you can choose either 4-bit or 2-bits. But if you not store this value, you can do the following computation. I think probably they can choose either you do the quantization or not. The activation.
But they do they consider, so for the whole network, do they consider a single activation function, or they may have different activation functions?
Activation functions.
Yeah, for example, some of them they are kind of ReLU, some of them they may be tangent, right? So
yeah, I think they do change the activation functions.
I'm just go ahead. Yeah.
Okay. So here, just summarize the overall algorithms to find the potential split point. And for each of the stored layers, they are assigned the bitwise for the stored layers. So they can come up with this big S to represent all the potential solutions. And then they will select the solution that with the minimum latency that measured by the simulators. And next, I will show the experiment results. So they do the simulation, like the simulator experiment and the real world experiment. So for the simulator experiment, they consider this edge device that followed this type of paper that they proposed a specific accelerator for the CNN networks. And also they consider the cloud device as the TPU. So based on both of these can be simulated from this ARM software. And this is their particular configurations here. And assume the up layer is a constant, the 3 magnet bit per second. So, and then they are going to compare the following benchmarks. The first one is the Chen-based splitting method that we introduced before. And the second one is the QDMP, which is the multi-cut based on the graph-based method. And also they consider two general method, which is the edge-only solution. We were going to quantize the entire network into 8 bits. And also for the cloud, we consider all the operation are done by 60 bits. So here is their first experiment. Consider the latency and versus the accuracy. So here they think of three scenarios where we introduced before. So for the cloud only, which means that this network is more be suitable to perform on the cloud, where the input image is much more smaller than the intermediate size. So you can see if we use the edge only solution, the latency will be much longer. And since all the network are performed on the cloud, so the accuracy is the same for the rest of the method. And also you can see a few networks are more suitable to just store on the edge itself. So in this case, the cloud latency will be the maximum. But since the specific network here is not the Chen based, so this neurosurgeon method will be not very optimal, suitable for this type of networks. And for the split operation, you can see the proposed method is always receive the smallest latency and the terrible accuracy results. And also they specifically discuss the different solution compared with their auto split and the graph-based method based on the full precision models. And as you can see here, here is the index for their optimal layer index in here. So if we consider do not do any quantizations, we can see the QD MP actually have the smaller latency, but since they do not consider the memory constraint, so the network are stored in the local device, consume a lot of memories. But if we consider the quantizations, and you can see after we consider 8 quantization, and the transmission, the bit is 1. So the overall latency will be greatly reduced compared with the existing work, and the memory cost is also very small in the edge device. So yes, and yes, and here is the real world testament. They consider a ULOAD V3 models to do the plate recognition application. So the model is stored in a camera. And as you can see, the proposed method is outperformed with the similar accuracy, and the latency is much more smaller. And also the storage size for the camera is pretty small compared with the existing solutions. So the TP here, I think just the uniform the quantization for 8 bits. And also they do the example when you change the network speed. So so for large network speed, you can save much smaller latencies. However, when in this case, when the network bandwidth is pretty large, but the accuracy is dropped, they claim that it's because probably those layers are more sensitive to the quantization. So they change to a different structures. And as you can see, the accuracy will be recovered with the smallest latency here. So, and that's it. So basically, they proposed the novel edge and the cloud splitting with the post-training quantization to further reduce the end-to-end latency and establish the introductive product. So you can find the code in the Huawei cloud. And that's it. Thank you. Any questions?
So for the mobile device, the constraint here is a very high level, right? It's not like, you know, you can do further hardware, say optimization or something, right? They just based on the existing resources of those mobile device hardware.
Yeah, yes.
Okay. I think this is like a cost find, but it point out a very good direction. We can further work on that. For example, we can work on with hardware people, right, to further improve the performance.
Yes.
But that's a very good direction, saying this kind of for drawing point, we can work with hardware people and networking people, right? We can say, how can we do the splitting and leverage wireless communication and cloud computing resources. But those hardware people, they can work on, say, how can they improve the computing capability and say memory efficiency or something as a mobile edge device point of view, right?
Yeah.
I think potentially there can be, okay, I will further discuss with you after the presentation. I think it can lead to a meaningful proposal or something. Okay. Okay, I'm going to stop recording here.